Good morning, everybody. For those of you who don't know me, I'm Richard Janicki. I'm the Director of Market Development at Mercury Systems. And I'm here today to talk to you about secure processing. Is it art? Is it science? Maybe it's magic. You know, a lot of the things that happen in secure processing are a bit hidden from public view. And we'll try and talk a little bit about even that part of the stuff. It's good to be back here in front of VITA and lots of friendly faces. But I wish it were under better circumstances, because we're under attack. Or more specifically, our computer systems are under attack. And these attacks form really two different types. One is the cyber attacks that you're all familiar with: worms, viruses, password cracking, spoofing Trojan horses, phishing even. The other type of attack are the ones that you can get when you get closer to physically close to to a system. You can maybe pull it apart, see what it looks like on the inside. You can use counterfeit parts. You can try and get in through a back door. You can even use side channel analysis to look at the magnetic waves in order to figure out what's really going on, how it reacts to external stimuli. Since Mercury is focused on defense systems, we're going to talk more about the second half, the part that happens when you have a deployed system, a fielded system, and you want to make sure that nothing bad happens if it gets into unfriendly hands. Does that ever happen? Yes. So not everything's out in the public, but here's one from about 15 years ago. There's a P-3. You probably remember a P-3 landed in China. Well, what happened was the P-3 was on a surveillance mission in international waters about 70 miles outside of Hainan Island in China, when it got buzzed by some Chinese fighter jets. Got buzzed a second time. It came around again for a third buzz, and one of the fighter jets happened to collide with the P-3. That fighter pilot died. The P-3 made a miraculous emergency landing on the island. The crew had 26 minutes to destroy all of the sensitive electronics and data. Part of that procedure involved pouring coffee on the electronics. As you can imagine, they may not have been entirely successful. But this is not the only incident. 2 years earlier, a similar something happened to an F-117 Nighthawk. This stealth fighter was participating in the NATO bombing of Yugoslavia. Seems pretty safe. You got stealth fighter going up against obsolete Soviet radar. What could go wrong? Well, somehow the Yugoslavs figured out that if they made the wavelength of the radar a little bit longer, you could actually see the plane. Not in normal circumstances, but when the bomb bay doors were open, all of a sudden, there it was. They said, hey, nobody told us it was invisible. Now, the plane actually came in, when it hit the ground, it was going slowly and inverted. So a large amount of the plane was still intact. It was carved up. Parts of it went to China, parts of it went to Russia. They kept the canopy and the pilot's helmet in the Belgrade Museum. So you can go and see it if you want. So yes, this stuff happens. It's not fake news. This is real stuff. But this was, these stories were from 15 years ago. So we must have fixed it by now. Sure enough, we have this great DoD directive, 52.44. Protection of mission-critical functions to achieve trusted systems and networks. Pretty powerful stuff. Everything you need to do is right in there, and it's accompanying appendices and references, and it gets pretty big, but it's there. And in fact, it was updated just this last summer to include more cybersecurity. So we must be fixed. Well, not exactly, because it's really hard, and nobody really does it. So almost all the systems platforms get a waiver. Turns out that up to this point, the only way to comply has been through old hardware that's been battle-hardened and tested, proprietary. It's usually about $1 million. It doesn't run very fast. Maybe it's 1980s technology. There's probably some good old Motorola processors in there, Jerry. And it doesn't go fast enough, so they sort of have the secure techniques in this secure part, and then they bolt on some modern processor servers next to it, and they get the offload of the non-sensitive stuff, but can only make it go so fast. So instead of that, you get a waiver, and you just hope that you don't fall into the wrong hands. So what's the cure? And I'm going to, again, focus mostly on the things that happen on the physical side. So we're here in New Orleans. Maybe we can find some magic pixie dust around the corner. Or in more modern times, we could say the answer is to build a wall. Maybe it's a firewall. Maybe it's a physical wall. That works really well if you're on the ground, maybe not so much if you're in the air or in the sea. I know it's a hard problem, so let's decompose it. Let's look at the parts of what it takes. Well, you're deployed, so of course you need to be rugged. We all know that part. I'm not going to talk much about that. Then you need to have a trusted supply. You need to make sure that when you're building the system, that it is what it's supposed to be, that nobody stuck a backdoor in there secretly, one way or another, either through hardware or software. And then you need the system integrity, the physical protection that if the system gets into the wrong hands or unfriendly hands, the ones that aren't intended for, that there's nothing that can really be learned. None of the secrets get out. And together, that makes a secure deployed system. So what do we have to worry about for system integrity? Well, we do have to worry about physical access. We have to worry about somebody taking it apart, looking inside, trying to figure out what it is, trying to see if they can make each component work, trying to download data or algorithms. We need to protect against maybe debug ports or other ways of accessing the system while it's physically running, seeing what you can learn, which also includes the side channel analysis I talked about, looking to see how the voltage changes, how the thermals change, watching all the different signals to see what you can learn. You can watch the memory bandwidth if you got the right tools. You can see what's going on. And of course, you can sit there in a modern processor, you got the boot code. What if you modified that boot code, stuck another chip in there? Can you get it to do something different? Can you get it to bypass the security protocols? On the trusted side, this is really the foundation of that security because, hey, if there was already a backdoor in the chip that you bought, you have some networking chips that were made in China, or you had some foreign national building the software, you need to be worried about, hey, you're fueling a system that's already started off being compromised. So it starts with the design phase, where you have, at least for the US military, you want US personnel working on the system in a vetted environment. Ideally, it's DMEA certified design facility, and that the whole facility has a really robust security infrastructure so that you're protected against hacking, people stealing the designs, or people taking a design and replacing it with a design that looks exactly the same but is a little different. Then you need to work with your suppliers, because it doesn't help if you protect yourself, but you're buying things from somebody who didn't use protection. So you need to have a trusted and managed supply chain. And for your software, you need to be able to go in and look at all the low-level software to see what's in there, to make sure that there isn't a backdoor. That includes the BIOS. I mean, some of these are hard. You need to be able to have an inspectable BIOS. You need it, and the network stack, too, from the ground up. All of the systems, all of the low-level system software needs to be inspectable and from a trusted source. And then you put it together, you build it. And when you build it, you again want it to be built by US persons and in a domestic DMEA certified manufacturing facility, ideally. And of course, the manufacturing, that's where they're loading the program, so another chance for having the wrong programs inserted if you don't have good cybersecurity. So these are all the ideals. How do you know if you're doing a good job, or how do you know if one of your suppliers is doing a good job? Well, one of the ways is you look to see who's won the James Cogwell Award from the Defense Security Service. Only about 1%, less than 1%, of all of the secure manufacturing and design facilities in the United States actually win an award like this. So that's really the cream of the crop. And now if you add in rugged and you put it all together, you can't have just one. You really need all three. There's lots of companies in this room who can do rugged. We know that. Many deployed systems. Trusted is quite a bit harder. In fact, even if we look outside of the beta space and outside of the military space in general, what about, just computer companies, server companies? Are any of them trusted? Well, it turns out, yes. I can think of one. And if anybody wants to know, come and talk to me afterwards, and I'll tell you who it is. There's one company it used to be IBM. Now, there's one company who's sort of the new de facto for the US government that actually has a fully trusted supply chain. But beyond that, it's pretty sparse. System integrity is actually even harder. There, it's only a couple of government laboratories, and the primes are starting to get a little bit better at this. But there's not much there. Mercury is actually the only company that has all three. And it's not proprietary like the current solutions. It's using beta standards. It's using 3U VPX and 6U VPX. We also have ATCA solutions. These are fielded in trucks and planes and ships. So secure and open don't have to be separate. They can go together. Secure solutions can also be very affordable. It's now, the same solution is now available as a secure rack mount server with very powerful Xeon multi-chip, multi-processor solutions. And of course, you need the storage that goes along with this, whatever form factor it is. And you have, so more than just self-encrypting drives, you have drives that are fully FIPS certified, and soon to be CSFC. Anybody know what that is? It's Commercial Solutions for Classified Applications. It's a new designation. So that's how you know you're secure. So in the end, maybe it is a little bit like magic. If you do all these things right, and you have your voodoo curses coming, they just bounce right off of a secure system. Don't give you entry. You get the secure prevents the reverse engineering, the trusted prevents the back doors, and the base of rugged means that you're preventing failures, even in operational environments, shock, temperature, or vibration. So secure, is it magic? Yeah, maybe. But I think it's also engineering. It's engineering that we can all do, and we should do. Thank you.